Welcome to Chapter 10, Molecular Geometry. Looking at molecular geometry, we use Vsepr, and that is valence shell electron pair repulsion theory. That means that those valence electrons that we were looking at repel each other, and that gives us our geometry, our electron shape, and then also our molecular shape. And the molecule will minimize the electron pair repulsions. How do we do it? Well, we draw the Lewis structure, and then we look at the electron geometry, and then finally we look at molecular geometry. Here are three ways to visualize it. The Lewis structure that we have been writing. Here is the electron geometry, and then this is just what the molecule looks like, the molecular geometry. The lone pairs take up more space, so you notice that these atoms are pushed slightly down. If you see a straight line, it's in the plane of the paper. Hash lines is into the paper, and wedge is projecting out. These are given so that you understand it, but you will not be required to use these lines. When we're talking about electron domains, we're talking about areas of electron. So it doesn't matter if it's a single bond or a double bond. Any group of electrons is a region or an electron domain. We're going to be looking at the center atom. So starting with two electron domains, we have a center atom, and there are two areas of electron around that center, and these represent those electrons. If both of them are bonding, you're going to get a linear. Our electron domain, so if we're looking at the electrons spread around, is linear. Our molecular domain is also linear, and here's an example. If we have three areas of electrons, three electron domains around the center atom, we have a trigonal planar because it is three and they're all in one plane. If, in this case, all three of those are bonds, then the molecular geometry is the same, trigonal planar. If we have two bonds and one lone pair, then we have a bent, or it's sometimes called a V-shape. If we have four areas of electrons, four electron domains, we have some possibilities. If all of them are bond pairs, then I have the same. So I have tetrahedral, and I have tetrahedral if they're all bond pairs. If I have one lone pair, that lone pair is going to take up more space, forces these down, and I have a trigonal, again tri for three, and pyramidal because this shape looks like a pyramid. Tetrahedral electron geometry also exists if there are two bond pairs and two lone pairs. This creates bent or V-shape, and that is why water is often drawn in this bent shape to illustrate how it actually exists in nature. So if we give this a try, we have water. So the first thing we'd have to do is draw this structure. We look, there are two bond pairs and two lone pairs. There are four electron domains. Water has a tetrahedral electron geometry or electron geometry because there are four areas around the center atom. Pause the video and write the Lewis structure for ammonia. Looking at the Lewis structure for ammonia, we see that there are four electron domains. So the electron pair geometry is tetrahedral. Three bonds and one lone pair. So if we go back to our chart, and you will have to know this chart, if I have three bond pairs and one lone pair, I have a trigonal pyramid. Remember, the difference between the electron pair geometry has all of the electron domains. Molecular is just the position of the atoms. Artificial sweeteners taste sweet, but they don't have any calories. So their taste and their calories are completely separate. We use table sugar, and it undergoes oxidation or combustion, and it releases a lot of energy. And it gives off carbon dioxide and water, which we breathe out through our lungs. But artificial sweeteners typically are not metabolized, and so they don't have any calories. And some are metabolized, but give a lot lower calories. So how do they work? The tongue has molecular detectors. The reason that things taste good is based on the molecule shape. So everything that we taste fit into this special area on our tongue, a taste bud, which is a protein called an active site. It actually detects those sweeteners. Artificial sweeteners taste sweet because they fit there just like sugar. Lots of times they also bond there more strongly than sugar. So you need 200 times as much sugar as you do an artificial sweetener. Not only are you using less, but it's metabolized in a different way, so you don't get the calories.